Calorimetry is the field of measuring heats of reaction. And it's going to open up some fun kind of problems we can solve, where we really have to understand what's going on and apply the first law of thermodynamics to get good answers. Thermochemistry, as we said already, is the study of heat and change in chemical reactions and systems. Historically, the calorie was used to measure energy. So a cal is a unit of energy, and it's defined as the energy required to raise the temperature of 1 gram of water 1 degree Celsius. So if you have a calories worth of energy, you can raise the temperature of 1 gram of water 1 degree Celsius. Big C calories are also called kilocalories. They're 1,000 little calories, and these are what we use to report food energy. So in my Captain Crunch, how many calories do I have? 109. So that's 109 big calories, or 109 kilocalories, or 109,000 little calories. The SI unit of heat, work, and energy is the joule, and there are 4.184 joules in a calorie. So any of the calculations we're doing here, we could use joules or we could use calories. Most often we use joules, but keep in mind, these are also acceptable. All right, some definitions. Heat capacity is the amount of heat required to raise the temperature of a substance 1 degree Celsius. And it can be anything. So heat capacity is an extensive property of matter. So it depends on the amount of stuff. Related is specific heat, little c, is the amount of heat required to raise the temperature of 1 gram of that thing by 1 degree Celsius. So this is also the definition of a calorie. Right? So the specific heat of water is 4.184 joules per gram degree Celsius. Intensive property, so it's independent of the amount of the substance that we're looking at. So pure gold, because it's pure, can typically have a specific heat. So it's 0.129 joules per gram degree Celsius. Things that aren't pure, it's harder to measure specific heats for those things because you can't grind this up and have an amount of solid gold elephant. You're stuck with the solid gold elephant, this thing. And so heat capacity is more appropriate here. So big C for this, heat capacity is 96.1 joules degree Celsius. So it takes 96.1 joules to raise this guy 1 degree Celsius. And the relationship is big C equals mass times little c. The units of heat capacity are joules per degree C, and if you multiply mass, which is grams, times the units of specific heat, joules per gram degree Celsius, grams cancel, and you end up with the same thing. So this is the relationship between the two. You might have seen, sometimes it'll show up as S. Little c, specific heat, will be an S instead of a C. Here's a list of some specific heats. Aluminum, gold, graphite has a relatively, graphite has a specific heat. How about that? Diamond. Water is quite a bit higher, and that's one of the special properties of water, is that it's really hard to raise its temperature. It holds thermal energy really well. Iron. All right. So of these, which would require more energy to raise its temperature? So if I had a pure copper pan and a pure iron pan, and they were the same mass, you can see that the iron would require more energy to raise its temperature, which on the flip side is it holds its temperature better, right? So if you want to have a nice even cooking pan, maybe this one's better, because once you get it to its temperature, it's not going to vary very much. On the other hand, the copper might be more responsive. So if I want to go from cool to hot, this guy's going to go a little bit faster. All right, so my friend gives me a gold elephant as a gift for helping him out. The elephant weighs 425 grams, and the heat capacity I measure, because, I had the equipment. If the specific heat of pure gold is 0.129 joules per gram degree Celsius, is the elephant really pure? So if you think about this, we can kind of approach this a couple ways. But basically, we want to see, are these two values related, right? If it's pure gold, then we should see that this relationship is true. So if big C, heat capacity, equals the mass times the specific heat, let's do it that way. Let's see if we get the heat capacity that we expect. So the elephant weighs 425 grams. So if we had 425 grams of pure gold, gram degree C, the specific heat or heat capacity would be 0.129. Oh no, is that right? Oh, it is 54.8 joules per degree C. So that is not the same as this. So tragically, it is not pure gold. The other way we could have done it was 425 grams. Little c equals 425 grams divided by big C. So that would be 425 divided by 96.1 joules degree C. Grams. Is that right? Hold on. Nope, wrong way. Sorry, bad math by me. I'm going to solve for little c. So little c equals big C divided by m, doesn't it? So, right, I looked at the units and realized I was going the wrong way. And I should probably say something, but it's okay to make mistakes, right? You just have to, I don't know, learn from them or something. 0.226 joules per gram degree Celsius. So again, as we expected, right, that is not the same as pure gold's specific heat. So sadly, not pure gold. We can calculate the heat in a process if we know the mass, specific heat, and change in temperature. So this relationship, or this relationship, allow us to calculate the heat. So Q equals MCAT is kind of how we say it, even though it's MC delta T, the change in temperature, or Q equals CAT, heat capacity times the change in temperature, where temperature change is T final minus T initial. So how much heat is given off when a 20-gram gold ingot cools from 94 degrees to 5 degrees Celsius? Specific heat of gold is that. All right, now write out the equation. C delta T, which really is MC T final minus T initial. So the mass is 20 grams. Specific heat of gold is 0.129 joules per gram degree Celsius. If you have time, including the units is good because it helps you keep track of whether you're making mistakes or not. Final degree temperature is 5 minus 94. And if I solve that, I get 20 times 0.129 times, oh, what's happening here? Times, right, and the T final minus T initial is just going to fix the sign. So negative 229.6 joules. Probably around here, this is 1 sig fig. Let's put a dot there to make it 2 sig fig. So we'll go to negative 230 joules. Okay, what does the negative sign mean? Means exothermic, right? So heat is released. And does that make sense? Yeah, because the ingot is cooling, right? It's radiating heat. So that would be a negative sign for my heat. How much heat is required to heat the golden elephant? Oh, from 20 to 1,064 degrees. Let's find out. So Q equals, here I have specific heat, so Q equals CAT. T final minus T initial. 96.1 joules degree C times T final, 1064, minus 20.0 degrees Celsius equals 6.1 times 1064. Minus, I didn't have to punch that in my calculator. That was sad. I get 100,328 joules of energy. All right, and so that's reasonable. Positive, right? Because we're heating it, so that makes sense, right? That would be an endothermic process. And it doesn't ask us to, but kilojoules are sort of a more convenient unit. So if I take kilojoules divided by joules, joules will cancel. I'll end up with kilojoules, and I'll get 100.3 kilojoules of heat are required to heat up the golden elephant, which would be 100. Oh, it would just be 100 kilojoules. Let's just say that. So what does the negative mean? Exothermic, right? A calorimeter is a device used to measure the heat involved in a chemical or physical process. So we have these equations, Q equals CAT and Q equals MCAT, but we have to have a way to measure the heat. And so a coffee cup calorimeter is a common way to measure heats of solutions or hot things. Like I can put a hot metal in there or something and measure the temperature change as it cools off. And so we use these coffee cup calorimeters to measure heat at constant pressure, which is the definition of enthalpy, the change in enthalpy. This is a fancier coffee cup calorimeter. Bomb calorimeters are designed with a bomb. This thing's called the bomb, right? It's this really strong, carefully milled container with a little cup, and you put your sample in there. Is it going to work? Yes. So you put your sample in there. You pump in oxygen, right? So this thing's filled with O2, and so what we're setting up is a combustion reaction. So you've got a whole bunch of oxygen, you've got your fuel source, the Big Mac, and then you have electrodes, so you ignite it, it burns, and where does the heat go? The first thing would heat up would be the bomb itself, and then it would start heating up this water around it, and then, further the container and stuff. So what we can do then is carefully measure the temperature change in the water and use that to determine delta T for our reaction. Over here, we just use our thermometer. This is constant pressure conditions, and constant volume conditions, and we've already learned that means we're measuring the internal energy, right? No energy can go towards work under these situation. So a simple example of calorimetry. What we have is a 110 gram piece of metal. Okay, so we'll pretend this is it. And it's at 486 degrees. Wow, it's pretty hot. Okay, so this guy has a temperature, 486.8 degrees C. And we are going to, we are going to put that in some water. And the water is at 20 degrees Celsius initially. So what's going to happen to the temperature of the water? It's going to go up, right? And the final temperature of water is 31.1 degrees Celsius. And the density of water is that. Okay, so let's see. What we can use is basically the first law of thermodynamics, right? If the system is only composed of the metal and the water, that means all the heat from the metal must go to the water or the calorimeter. So what we can do then is calculate, we know that Q of the metal, right, the heat associated with the metal, plus the heat of the calorimeter, right, the water and the coffee cup or whatever it is, has to equal 0, right? Sometimes, well, I'll say that in a second. So I'm solving for the Q of the metal, the heat of the metal. What I can do is I can substitute in for MCAT. In this case, the calorimeter is just water. We're just going to assume it's just water. So we can use MC delta T for water. So the mass of water, didn't give me mass, but how much water do I have? I have 415 milliliters, and I know the density of water is 1 gram per milliliter. Those will cancel, and I get grams. So 415 grams of water. The specific heat is one that we know, 4.184 joules per gram degree C. And delta T is, let's see, for the water, right? You have to be careful what you're talking about. And this is all for the water. Is T final of the water is 31.1 degrees C minus 20.0 degrees C equals 0. And then I punch that in and I can solve for Q metal. So 415 times 4.184 was that times 11.1, right? Equals 19,273. But I need to subtract it across, so I'm going to get the negative of that. 19,273 joules. If we wanted to care about sig figs, we should probably go to something like negative 19,300 joules. That is the heat that's released by the metal. And we expect that to be exothermic, and it is. All right, so this is how we can do these calorimetry problems. So we have a coffee cup calorimeter, right, which is just filled with water. All right, we put something in it. The heat given off by that thing is absorbed entirely by our system, water in this case. So what we know is we can add these things up to get 0. If we know some of the components of the system, we're able to solve for the thing. what happens here? Let's see. Oh, this is what I was saying here. So I like to write it this way: Q metal plus Q water, Q calorimeter equals 0. You can subtract Q calorimeter across both sides, and you get Q metal equals negative Q calorimeter. Either way, means the same thing. All right, so what's the specific heat of the metal? So again, we're starting with Q metal plus Q cal equals 0. Q of the metal, we can write M C delta T plus MC delta T equals 0. Oh, actually, we already know this number, so we don't need that. So MC, we're solving for C for the metal, so I want to remember that. All right, let's just substitute the things in that we know. The mass of the metal is 110 grams. C is what we're solving for. T final for the metal is the same as the water, right? They're a system together. Their temperatures will end at the same place. Minus 486.8. Plus, we already solved this, so negative 19300 equals 0. Oops. So that's cute. Am I doing this right? Yeah, but it's positive. Right, so I could plug these numbers back in there, right? They're the same numbers, so I'm going to get the same value. All right, so we're going to solve for C. All right, so I'm going to take that across. So negative 19300, we know that, okay, equals 110. Let me combine those. Hold on. Oh, come on. All right. So 31.1 minus 486.8 equals negative 455.7 times 110. It's the mass of the metal. So this and this give me negative 50127. We still have C, which we're solving for. So I divide both sides by negative 50,127. And I get C equals 0.385. Whoa, I'm switching back. Specific heat, joules per gram degree C. All right. So if this was one of our metals, we could see what it is. And oh my gosh, it's copper. Nice work by us. All right, so this is an easy example of calorimetry where we know the system, right? The energies of the system add up to be 0. So if I can solve for one of these things, I can solve for the other thing. Let's see, so more complex examples, we have to consider more examples, more factors. And these are good because they force you to think about stuff, all right? And thinking about stuff is good for you. So if we look at a coffee cup calorimeter, let's think about all the possible things. So let's say I put my hot metal in there again. So here's my piece of hot metal, all right? What would absorb that heat? First, we could have the Q of the, so here's Q of the metal, right? Plus Q of the water in there, right? I might say Q of the calorimeter. If I consider this guy, right, as a separate part, this coffee cup will change, has to change temperature, so that could be included. 0, right? So this is about as complicated as it can be. Sometimes the problems will tell us just ignore the calorimeter or something like that, or these are combined. So we'll do that. And basically with coffee cup calorimeters, we can only measure changes in temperatures of hot things when we put them in, or certain reactions like dissolving solutions, dissolving something in water, or mixing an acid and a base, which is exothermic, right? That'll change the temperature and we can measure those heats of reaction. So in lab, typically we do these kind of experiments, and they work pretty good. And remember, this is constant pressure conditions, right? The atmospheric pressure is pushing down, and it doesn't change, even if gases are released here. So delta H is what we're solving for. The Q at constant pressure is the enthalpy of the reaction. The bomb calorimeter, let's think about all the parts in there. So the simplest system would be the Q of the calorimeter, which would be the whole thing, plus the Q of the reaction, right? The thing being burned equals 0. The calorimeter, though, could be broken up into this guy, the bomb. So it could be Q bomb plus Q water, right? The water is going to heat up next as that hamburger burns. Then we could say that's about as far as you go. You could start including calorimeters. If you actually do this experiment, there's so many different things you have to control for. Let's see, Q reaction. In this case, I'm going to say Q reaction. I'm calling the reaction combustion. Right? We'll do that sometimes because that's what's actually happening, right? We're burning the samples in there. And so this is what you do, right? If we wanted to get the energy of Captain Crunch, we'd weigh some Captain Crunch, we'd stick it in there, pump it full of oxygen, burn it, and we would get a heat change. We'd be able to calculate the heat of that reaction, and that would be the calories in Captain Crunch. Because we're measuring this at constant volume conditions, this is called the change in internal energy. All right, so now we're going to practice thinking about all these things.